In this video, we're going to have a look at forced vibrations and resonance in simple harmonic systems. If you've got someone on a swing, you can force them to go higher and higher in their swing by pushing them. You can apply an external force to make them oscillate in a way that they wouldn't naturally. And in this scenario, the person doing the pushing is called the driver. That's just the thing that provides the periodic force that forces a vibration. And a forced vibration is just when you apply a periodic force to an oscillating system. Now, a classic example of this is a mass suspended between two springs. Here, a signal generator allows us to vary the applied frequency of the periodic force. And that signal generator tells the driver, the thing providing the periodic force, at what frequency to oscillate. Now we're going to make some observations of what happens as I increase the frequency of this oscillating system. So as the frequency increases, we can see that the amplitude of the oscillation starts to increase. And this will continue all the way up until a particular optimum frequency is reached. And in this case here, the frequency at which we get maximum amplitude is at 3.33. Once we go beyond this optimum frequency, we can see that the amplitude starts to decrease again, getting smaller and smaller as time progresses. And as the system is approaching the maximum amplitude, you get a phase difference between the driver here and the oscillation of your system. From minimum amplitude all the way up to the maximum, it will increase from 0 to pi over 2. And it will be pi over 2 phase difference at maximum amplitude. As you go beyond this maximum amplitude, as the amplitude starts to decrease again, then this phase difference increases further from pi by 2 to pi. But why is that? Well, you might remember that for a simple harmonic motion system, we had to draw the graphs for displacement, velocity, and force/acceleration. Since force is mass times acceleration, the graphs for the two are the same. And for a displacement time graph, we get a cos function. Since velocity is the derivative of a displacement, that means the whole graph shifts pi by 2 to the left to give us our velocity time graph. And since acceleration is the derivative of velocity, that velocity graph shifts by 1/4 of a cycle, or pi by 2 radians, to the left again, to give us a minus cos graph. Now, at maximum amplitude, we said the phase difference between the displacement of the system and the driving force is pi by 2 radians, as you can see in this graph on the right. And this means that the periodic force at this point will be in phase with the velocity, producing this maximum amplitude. As you go beyond that, the phase difference increases from pi over 2 to pi radians. But at the point of maximum amplitude, the two, that is the graph, the periodic force and the velocity, will be in phase. And when this happens, we say the system is in resonance. It is vibrating at its maximum amplitude. Now we call the frequency at which resonance occurs the resonant frequency. Now, there's another type of frequency that we need to be aware of, and that's the natural frequency. All systems will have a natural frequency at which they will easily vibrate. And in this video here, I have got a signal generator attached to a driver, which has got 3 bits of metal attached in the middle to effectively give us 6 different lengths of metal. And as we change the frequency, you will see that different lengths of metal will vibrate with different amplitudes. And when we hit the natural frequency of one particular length of metal, that length of metal will vibrate at maximum amplitude. So in this video we can see we're cycling through to get to the natural frequency, or the frequency at which objects will naturally want to vibrate. Now, if we were to take one of those pieces and have a look at how its amplitude varies with frequency as you approach this natural frequency, let's say we take one of the strips that has a natural frequency of just over 20 Hertz, you will get an increase in amplitude and a phase difference increasing from 0 to pi by 2 until it hits that natural frequency. And then the amplitude will tail off as you go above it. What will be the effect of different types of damping? Well, if I've got a very lightly damped system, then I will get a bigger maximum amplitude, but I will also get the point happening, or the peak, closer to the natural frequency of the system. So I get a higher amplitude and a narrower peak that's closer to the natural frequency. If, however, I'm heavily damping the system, this means that I am trying to take the vibration out of it, and therefore the amplitude at its maximum will be lower, and I get a much wider peak, or I get it peaking less close to its natural frequency. And this is a set of graphs that you need to be able to reproduce. So for an oscillating system with little to no damping, when it's at resonance, the applied frequency of the periodic force is going to be equal to the natural frequency of the system. And this has some very real-world consequences. Barton's pendulum is a classic that is shown in the classroom. And in this setup, I have got a driving pendulum, quite a massive one of specific length, and several other pendulums further along this line that joins them. Now, when the driving pendulum is set oscillating, in this case here you can see it just at the edge, energy is transferred from the driver to the other ones through the string connecting them at the top, submitting them all to a forced oscillation. And we can see that the amplitudes of these oscillations vary. The pendulum that has the same length as the driving pendulum, in this case the black one, will have the largest amplitude. And that's because it has the same period and therefore natural frequency as the driver pendulum. So here we can see that the black pendulum is really swinging, far more than the others, and when we change the perspective on the video, you can see just how marked that increase in oscillation is, that increase in amplitude. And that's because the black pendulum has the same length and therefore natural frequency as the driver. So it is in resonance with the driving pendulum. And a classic example of this in the real world is the Tacoma Bridge collapse. Now in 1940, a bridge that had only been open for a few weeks started to oscillate wildly from side to side. And it turns out that what had happened was that wind passing through the canyon over which it was built was gusting at the same frequency as the resonant frequency of the bridge. And well, to see what happened, I'll just let the video describe.